All around us, a new kind of intelligence is beginning to operate. It does not think like a human. It does not have a body. It does not have a voice. Instead, it exists as a complex web of algorithms and data, running silently on vast networks of computers. This is the world of artificial intelligence. It promises to reshape industries. It will accelerate scientific discovery. It will change how we interact with technology, from the recommendations on our screens to the navigation systems in our cars. Its influence is already deeply embedded in the fabric of modern life, often in ways we do not see or consciously acknowledge. This digital revolution is fueled by something very physical and very real: electricity. Each query, every calculation, every model trained, all require a significant amount of electrical power. As the capabilities of AI expand, so does its appetite for energy. This is not a small or incremental increase. The growth is exponential, creating a demand that is beginning to place a measurable and unprecedented strain on the very systems that power our world. The silent hum of progress is growing louder, not in our ears, but on the grids that sustain our societies, pushing them towards limits they were never designed to handle. Our electrical grids are one of the greatest engineering achievements of the last century. They are vast, interconnected networks designed to deliver reliable power to homes, businesses, traditional industries. These systems were built for a predictable world. Their architecture was based on decades of data about when people wake up, when factories turn on, when cities go to sleep. Planners could forecast demand with a high degree of accuracy, ensuring supply met a human-paced society. However, artificial intelligence does not operate on a human schedule. It does not follow the predictable rhythms of day and night. An AI training model can run at maximum capacity for weeks or months, drawing a massive and constant load of power. A popular generative AI service can cause demand to spike suddenly and unpredictably as millions of users interact with it at once. This new type of demand is different. It is volatile, it is intense, and it is sustained in ways our grid was never intended to support. The established patterns are being broken by a new kind of consumer. The strain is not just a matter of generating more electricity. It permeates every component of the system. These facilities can require as much electricity as a small city, overwhelming nearby substations and transformers that were designed for much lighter loads. The stress then travels up the chain to the high-voltage transmission lines that carry power over long distances. And sudden massive draws from AI clusters can create bottlenecks that threaten regional grid stability. We will analyze the physical limits of aging equipment and the logistical challenges faced by utility planners. They are caught between the slow, deliberate pace of infrastructure development and the breakneck speed of technological advancement. The gap between digital demand and physical capacity is widening. We will trace the flow of energy from the power plant to the processor, revealing hidden vulnerabilities in a system we all depend on, now tasked with powering not just our world, but the intelligence of the machines within it. At the heart of the artificial intelligence boom are the data centers. These are the physical homes for the digital minds we are creating. From the outside, they appear as vast, featureless buildings, often located in remote areas where land and power are cheaper. They are the modern factories of the 21st century, but instead of producing cars or consumer goods, their assembly lines are made of servers, and their product is computation. These facilities are designed for one purpose: to house and power tens of thousands of computers operating in unison. They are the engine rooms of the information age, and their energy consumption is staggering, far exceeding that of any traditional commercial building. The power consumed by a single large-scale data center is difficult to comprehend. A typical facility can require anywhere from 50 to 100 megawatts of electricity, and the newest hyperscale centers built for AI are pushing beyond that. To put this into perspective, 100 megawatts is enough to power approximately 80,000 homes in the United States. A single building dedicated to processing data can have an electrical footprint equivalent to that of a small city. As the demand for AI services grows, technology companies are building more of these digital factories, each one adding another city-sized load onto an already burdened electrical grid. This is not a gradual increase. It is a step change in industrial power demand. This enormous power draw is not just for the computers themselves. A significant portion of the electricity, often as much as 40%, is used for cooling. The processors that run complex AI algorithms generate an immense amount of heat. To prevent them from overheating and failing, the entire facility must be kept at a constant cool temperature. This requires massive industrial-scale cooling systems, including chillers, pumps, and enormous fans that run continuously, 24 hours a day, 7 days a week. This secondary power load, dedicated solely to managing waste heat, adds another layer of constant, intensive demand that distinguishes data centers from nearly any other type of electrical consumer. The location of these facilities is therefore a critical decision, driven almost entirely by access to two resources: high-speed fiber optic cables and, more importantly, massive amounts of stable, reliable electricity. Utility companies in regions like Northern Virginia, Phoenix, and Dublin have seen their long-term demand forecasts shattered by the sudden arrival of these power-hungry clients. This creates a fundamental conflict between the speed of digital expansion and the physical realities of power generation and delivery, a tension that is now reaching a critical point. To understand the energy demand of artificial intelligence, we must look inside these digital factories. A traditional data center is filled with standard servers, used for tasks like web hosting, data storage, and corporate networking. These tasks require processing power, but the load is often variable and distributed. An AI data center, however, is a different kind of beast. It is built around specialized hardware designed for the unique mathematics of machine learning. The workhorses of these facilities are not central processing units, or CPUs, but graphics processing units, or GPUs. These powerful chips, originally designed for rendering video game graphics, are exceptionally good at performing the parallel calculations needed for AI. A single high-end GPU server, packed with multiple chips, can consume between 10 and 15 times more electricity than a standard server. A single rack of these AI servers can draw over 100 kilowatts of power, a density that was unheard of just a few years ago. This concentration of power in such a small physical space creates immense challenges for electrical distribution and cooling within the building itself. The standard electrical wiring and cooling systems of older data centers are simply not equipped to handle this level of power density, forcing a complete redesign of the internal infrastructure of these facilities. The difference in load is not just about the peak consumption, it is about the nature of the work. AI workloads, particularly during the training phase, do not have idle periods. When a large language model is being trained, it pushes thousands of these GPUs to their maximum processing capacity and holds them there for extended periods. This creates a high, flat, and unrelenting demand for power. This type of load profile is more akin to a heavy industrial process like an aluminum smelter than to any previous form of information technology. The power distribution units that deliver electricity to each rack must be larger. The backup power systems, including massive batteries and diesel generators, must have the capacity to support these enormous loads in the event of a grid failure. The cooling systems must be able to dissipate heat at a rate that is an order of magnitude higher than before. Every component, from the utility connection at the edge of the property to the individual power cable plugging into a server, must be engineered for a level of intensity that the computing industry has never before seen. The most energy-intensive process in the AI lifecycle is training. This is the stage where a model learns from vast quantities of data. For a large language model like those that power generative AI chatbots, this involves processing trillions of words, images, or lines of code. The model adjusts its internal parameters millions of times, gradually refining its ability to recognize patterns and generate coherent responses. This process is a computational marathon, requiring the coordinated effort of thousands of specialized processors running at full tilt, non-stop, for weeks or even months on end. Quantifying this consumption reveals the scale of the challenge. Training a single, state-of-the-art AI model can consume multiple gigawatt-hours of electricity. A gigawatt-hour is 1,000,000 kilowatt-hours. It is enough energy to power thousands of homes for a month. And this is not for a finished product. It is the energy required for just one training run. As models become more complex and are trained on ever larger datasets, this energy requirement continues to climb. The competitive race to build bigger and more capable models is, in effect, a race to consume more and more electricity in shorter and shorter periods, creating a direct link between AI progress and energy demand. This massive sustained load places a unique and difficult strain on the power grid. Unlike the fluctuating demand of a city, which rises in the morning and falls at night, the demand from an AI training cluster is a solid, unwavering block of power consumption. For a utility provider, this is a multi-megawatt load that appears suddenly and remains constant for a month, only to disappear just as abruptly once the training run is complete. This pattern does not align with traditional grid management strategies, which are based on predictable daily and seasonal cycles. Furthermore, the training process is highly sensitive to power interruptions. A momentary loss of power can corrupt a training run that has been going for weeks, forcing researchers to start over from scratch. This wastes all the energy consumed up to that point and incurs significant financial costs. To mitigate this risk, data centers rely on extensive backup systems, but their primary demand is for exceptionally high-quality, uninterrupted power from the grid. This need for near-perfect reliability, combined with the sheer size of the load, elevates AI training from being just another customer to a critical piece of infrastructure that grid operators must protect, often at the expense of other parts of the system. After a model is trained, it enters the next phase of its life: inference. This is the process of using the trained model to make predictions, generate text, or analyze new data. Every time you ask a chatbot a question, translate a sentence, or use an AI-powered image generator, you are initiating an inference task. While a single inference query consumes far less energy than the training process, the sheer volume of these queries creates a different, but equally significant, energy challenge. The marathon of training gives way to a continuous sprint of countless individual calculations, each one taking a small sip of power. A popular generative AI service might handle hundreds of millions of user requests every day. When multiplied by billions of users worldwide, these tiny sips of electricity accumulate into a massive, continuous river of power demand. Unlike the static block of a training run, the inference load is dynamic and spiky. It can surge unpredictably based on viral trends, news events, or the time of day when most users are online, creating a volatile demand profile. This volatility presents a major headache for grid operators. Power grids are designed for stability and must constantly balance supply with demand in real time. A sudden, unexpected surge in inference-driven demand across thousands of data centers can destabilize this delicate balance. This forces utility operators to quickly ramp up generation from reserve power plants, which are often less efficient and more expensive to run. As artificial intelligence is integrated into more and more applications, the baseline inference load will only grow. It is becoming a permanent new layer of electricity demand that did not exist 5 years ago. This load is active 24/7, spread across the globe, and subject to unpredictable spikes. For energy planners looking decades into the future, this is a profound source of uncertainty. They are now tasked with forecasting not only economic growth and population changes, but also the adoption rate of new AI technologies and the unpredictable behavior of their users. The collective activity of billions of people interacting with machines is creating a new and powerful force on the global energy system. Most organizations and developers do not build their own data centers to run AI. Instead, they rent computational power from a handful of giant technology companies. Through cloud computing services, these cloud providers have built the hyperscale data centers that form the backbone of the modern internet, and now, the AI revolution. They are tapping into the immense, centralized infrastructure of the cloud. This has accelerated the adoption of AI, but it has also concentrated massive energy demand into the hands of just a few corporate players. That concentration has profound implications for regional power grids. Cloud providers are engaged in an arms race to build out AI capabilities, which means securing enormous amounts of power. They are now the single largest drivers of new electricity demand in many parts of the world. In some utility territories, one cloud company's expansion can account for a region's entire projected load growth for the next decade. These companies negotiate directly with utilities for power purchase agreements, often demanding hundreds of megawatts or even gigawatts of new capacity, an amount equivalent to what a nuclear power plant can produce. To meet it, utilities must embark on massive infrastructure projects. This includes building new high-voltage transmission lines to bring power to data center campuses and upgrading local substations to handle the immense load. These projects are expensive, time-consuming. They face regulatory hurdles and community opposition, creating a bottleneck between the cloud's thirst for power and the grid's ability to supply it. This dynamic creates a new kind of power struggle. The handful of companies that control the cloud have immense leverage over utilities and local governments. They can choose where to build their next billion-dollar campus based on the cheapest power, or the most abundant power, or the most reliable power. This pits states against each other, and even countries, competing to attract these investments by offering tax breaks and promising massive upgrades to energy infrastructure. The quiet, behind-the-scenes negotiations over power capacity for cloud data centers are now shaping the future of energy systems and economic development around the globe, driven by the relentless computational demands of AI. While the giant data centers represent the most visible concentration of AI's energy appetite, a new and more distributed form of consumption is emerging at the edge. Edge computing refers to processing data closer to where it is generated, rather than sending it all the way to a centralized cloud. This includes the powerful onboard computers in autonomous vehicles, the smart sensors in a factory, the diagnostic equipment in a hospital, or even the high-end smartphone in your pocket. As AI models become more efficient, they are being deployed on these smaller, localized devices to enable real-time decision-making without the delay of communicating with a distant server. Each of these edge devices consumes a relatively small amount of power on its own. The AI chip in a smartphone might only draw a few watts when it is active. However, this is a classic case of distributed, large-scale consumption. There are billions of such devices in the world, and that number is growing rapidly. When you multiply a few watts by billions of devices, the aggregate electrical load becomes substantial. This is a form of unseen energy consumption. It does not appear as a single, massive load on the grid, but as a subtle, widespread increase in demand across millions of homes, businesses, and public spaces where these devices are charged and operated. This shift to the edge changes the shape of AI's power demand. Instead of being concentrated in a few dozen hyperscale locations, the load becomes dispersed across the entire electrical grid, right down to the low-voltage distribution networks that serve individual neighborhoods. This creates a different kind of stress. It is not about overwhelming high-voltage transmission lines, but about adding a persistent, slowly growing base load on local circuits. The transformers on utility poles and the wires that run to each house were not designed with the assumption that every home would eventually contain multiple AI-powered devices, each drawing a continuous trickle of power for processing and charging. This distributed load is also much harder to measure and manage. A utility can meter the consumption of a single data center, but it is far more difficult to isolate the portion of a household's electricity bill that comes from its collection of smart devices. As AI becomes more deeply embedded in the consumer electronics we use every day, its energy footprint becomes diffused into our collective background consumption, appearing as a slow, almost imperceptible rise in the baseline energy needed to power a modern society. That is the really tricky part. The journey of electricity from a power plant to an AI processor is long and complex, involving thousands of kilometers of wires and multiple stages of voltage conversion. The final, and often most vulnerable, part of this journey is the local distribution network. These are the familiar power lines and underground cables that run along our streets and connect directly to homes and businesses. This part of the grid was designed decades ago for a world of predictable, low-density loads like lighting, appliances, and small commercial enterprises. It was never envisioned to support the concentrated, industrial-scale power demands of facilities like modern data centers, which are now being built in these same suburban and rural areas. When a multi-megawatt data center connects to a local distribution grid, it acts like an enormous vacuum, pulling a vast amount of electrical current through circuits designed for a fraction of that load. The existing wires, which may have served a small community or a business park for 50 years, are suddenly tasked with carrying the power equivalent of a steel mill. This immense current generates heat, causing the wires to sag and lose efficiency. It pushes every component on the local circuit, the fuses, the switches, the connectors, to its absolute design limit, and often beyond. This creates a critical point of failure right at the doorstep of the AI facility itself. The consequences of overloading these local networks are immediate and tangible. The most direct risk is equipment failure leading to a localized blackout. A single fuse blowing on an overloaded feeder line could take the data center and the entire surrounding neighborhood offline. For the data center, this is a catastrophic event. For the community, it is a disruptive and potentially dangerous loss of power. Utilities are forced into a reactive mode, performing emergency upgrades and replacing components on an accelerated schedule. They must reinforce these local pathways, often by running new, thicker cables dedicated solely to serving the data center. This intense stress on local distribution infrastructure also has significant financial implications. The cost of upgrading these last-mile connections is substantial, involving expensive equipment, skilled labor, and disruptive construction work. These costs are ultimately borne by the utility and are often passed on to the entire customer base through higher electricity rates. In this way, the community that hosts a large data center can find itself subsidizing the immense power needs of a single facility. The arrival of an AI-driven load is not just a technical challenge for the grid, it is an economic event that reshapes the financial landscape of local power delivery for everyone. It's a lot to digest. At critical points in the distribution network sits a humble but essential piece of equipment, the transformer. Its job is to step down the high voltage from regional lines to a lower usable voltage for consumers. Whether mounted on a pole or sitting in a green metal box on the ground, these devices are the gatekeepers of power for every building. Like the wires they connect to, transformers are rated for a specific capacity. They are designed to handle the normal, fluctuating loads of a neighborhood or a business park, with enough headroom for occasional peaks. But the constant, high-intensity demand of an AI data center is a completely different challenge that pushes these devices into a state of perpetual stress. A transformer dealing with a load far beyond its design specifications is an unhappy piece of machinery. The immense electrical current flowing through its internal windings generates a tremendous amount of heat. When they are consistently overloaded, this cooling system cannot keep up. The internal temperature begins to rise relentlessly, day after day. This sustained thermal stress causes the insulating materials inside the transformer to degrade, dramatically shortening its lifespan. A transformer that was meant to last for 40 years might fail in less than 5 under such conditions. These are not off-the-shelf items. Large-scale transformers are complex pieces of heavy equipment with long manufacturing lead times. It can take more than 1 year, sometimes several years, to procure a replacement for a large substation transformer. The sudden spike in demand from the AI industry has created a global supply chain bottleneck for these critical components. Utilities are now finding themselves in a queue, waiting for new transformers while their existing fleet is being cooked from the inside out by the unrelenting power draw of data centers. The failure of a large transformer is not a quiet event. It can be explosive, resulting in fires, oil spills, and widespread power outages that can last for days or weeks until a replacement can be installed. For a grid operator, the risk of a cascaded failure becomes very real. If one overloaded transformer fails, the load it was carrying is automatically shifted to neighboring transformers, which are likely already under stress from the same data center. This can create a domino effect, where one failure triggers another, leading to a much larger and more difficult to manage blackout. The humble transformer has become a critical vulnerability in the grid's ability to support machine intelligence. So yeah, that's the crux of it. If local distribution lines are the city streets, then electrical substations are the major intersections. These facilities are where power is rerouted, controlled, and converted between voltage levels. They are the nerve centers of the regional power system, connecting the high-voltage transmission network to the lower-voltage distribution networks that serve communities. A typical substation is designed to balance flows and serve residential, commercial, and light industrial customers, built with a specific capacity in mind from decades of planning. The arrival of a hyperscale data center breaks that planning model. A single AI campus can demand more power than the entire substation it connects to, like building a new superhighway and dumping its traffic onto a 2-lane road. The substation becomes an immediate and severe bottleneck. Circuit breakers, switches, and transformers are forced to handle double or triple their design load. The substation becomes a point of extreme congestion and high risk. To accommodate the load, the substation needs a complete, expensive overhaul. Not just a new switch, often a total rebuild. Acquiring more land, pouring concrete foundations, installing larger transformers, and installing higher capacity circuit breakers and more complex control systems. These projects cost tens or hundreds of millions of dollars. The timeline, design and permitting, construction and commissioning, can span 5 to 7 years. Tech builds data centers and demands power in under 2 years. That mismatch creates significant vulnerability. Utilities may operate substations beyond safe limits, implement temporary fixes, and rely on operational gymnastics for years. This raises blackout risk for the data center and every other customer. The hospital, the schools, the homes in the area face reduced grid reliability. The substation, critical public infrastructure, is effectively privatized by one industry's needs. Before electricity reaches a local substation, it must travel, often for hundreds of kilometers, from power plants through the grid's major arteries, the high-voltage transmission corridors. These networks of massive towers and thick cables are the backbone of the entire electrical system, moving huge quantities of power from where it is generated to where it is needed. Like highways, these corridors have a finite capacity. They can only carry so much electrical current before they begin to overheat, sag dangerously, or become unstable. The rise of AI data center clusters is creating unprecedented levels of congestion on these transmission arteries. A region like Northern Virginia, the world's largest data center market, now has such a high concentration of these facilities that the transmission lines feeding the area are consistently running at or near their maximum capacity. This means there is no more room on the highway. Even if a utility could build a new power plant to generate more electricity, there is no available path to deliver that power to the data centers that need it. The grid has become transmission constrained, a technical term for a system-wide traffic jam, This congestion has severe consequences for grid stability and economics. When a major transmission line is maxed out, grid operators lose flexibility. If a power plant elsewhere on the grid suddenly goes offline, they may not be able to reroute power through the congested corridor to prevent a blackout. It also distorts the energy market. Cheaper power from wind farms or hydroelectric dams located far away cannot be delivered to the demand centers, forcing utilities to rely on more expensive and often dirtier power plants located closer to the load. The result is higher electricity prices and increased carbon emissions, all because the system's arteries are clogged. Solving this problem requires building new high-voltage transmission lines, one of the most difficult and contentious infrastructure projects to undertake. These projects cross vast stretches of land, involving complex negotiations with hundreds of private landowners, lengthy environmental reviews, and immense political challenges. A single major transmission project can easily take over a decade to plan and build. The slow, arduous process of expanding the grid's backbone is completely mismatched with the explosive, concentrated growth of AI-driven electricity demand. The system's long-haul capacity is now a primary limiting factor in the continued expansion of artificial intelligence. Much of the electrical grid that powers our modern world is a product of a different era. A significant portion of the transformers in service today were installed in the 1950s. A significant portion of the circuit breakers in service today were installed in the 1960s. A significant portion of the transmission lines in service today were installed in the 1970s. These components were built to last, engineered for a projected lifespan of 40 to 50 years. This means that a substantial part of our grid infrastructure is now operating at, or well beyond, its intended retirement age. For decades, utilities have managed this aging asset base through careful maintenance, refurbishment, and gradual replacement programs, balancing investment against the slow, predictable growth in demand. This delicate balancing act is being completely upended by the sudden, intense demands of artificial intelligence. The new loads from data centers are not just a matter of increased quantity, they are a catalyst that accelerates the aging process of already old equipment. The wear and tear that might have accumulated over a decade can now occur in a single year. The grid is not just being used more, it is being consumed at a faster rate, dramatically shortening the remaining life of its most critical parts. This accelerated aging crisis forces utilities into a difficult position. They are now faced with the need to replace massive amounts of equipment on a compressed timeline, a task for which they are neither funded nor staffed. The industry is shifting from a proactive maintenance posture to a reactive, emergency-driven one, a far more expensive and less reliable way to run a critical infrastructure system. The physical reality is that you cannot simply run a software update on a 60-year-old transformer. You cannot download a patch for a corroded transmission line. The world of hardware, of steel, copper, and concrete operates on a different timescale from the world of software. The rapid advancement of AI is colliding with the slow, physical decay of the legacy system it depends on. This collision is creating fractures throughout the grid, exposing the vulnerabilities of a system that has been taken for granted for decades, revealing the hidden costs of powering a new machine age with last century's infrastructure. At the core of the grid's struggle is a fundamental conflict of speed. The world of technology, and particularly AI, operates on a timescale measured in months. A new generation of AI chips is released every 18 months. A company can decide to build a new data center and have it operational in under 2 years. The culture is one of rapid iteration, exponential growth, and moving fast and breaking things. In stark contrast, the world of energy infrastructure operates on a timescale measured in decades. The process of planning, permitting, and building a major power plant or a new transmission line is a slow, deliberate, and complex undertaking. It involves long-term demand forecasting, extensive environmental impact studies, complex regulatory approvals at multiple levels of government, and often contentious public consultations. A 10-year timeline for a single major project is considered ambitious. This temporal mismatch creates a massive planning gap. Utility planners, who are accustomed to forecasting demand growth of 1 or 2% per year, are now being confronted with requests for a single facility that will increase their total system load by 10 or 20% in less than 24 months. Their traditional models and processes are completely inadequate for this new reality. It is like trying to steer a massive cargo ship to chase a speedboat. As a result, planning is breaking down and being replaced by reaction. Utilities are no longer in control of their own systems development. They are being pulled along by the demands of their largest new customers. This reactive posture is inherently inefficient and risky. It leads to rushed, suboptimal decisions, cost overruns, and a grid that is built piece by piece in response to crises, rather than as a coherent, resilient, and intelligently designed system. The speed of the digital world is overwhelming the capacity of the physical world to adapt, and the gap between the two represents one of the greatest hidden threats to the stability of our energy supply. The electrical grid is a deeply interconnected system. It is not a collection of independent parts, but a single, continent-spanning machine where an event in one location can have immediate consequences hundreds of kilometers away. This interconnectedness is normally a source of strength, allowing power to be shared and routed around problems. However, when the system is under extreme stress, this same property becomes a source of profound vulnerability. The localized stress placed on a single transformer or substation by an AI data center does not remain a local problem. It radiates outwards, creating risks for the entire regional grid through a phenomenon known as a cascading failure. A cascade begins with a single fault. An overloaded transmission line sags into a tree and shorts out. A substation transformer, cooked by months of overuse, finally fails. The grid's automated protection systems instantly react, rerouting power around the failed component. But if the surrounding parts of the grid are already heavily loaded, which is increasingly the case in areas with high concentrations of data centers, they cannot handle the sudden influx of diverted power. This pushes a second component past its limit, causing it to fail as well. In a matter of seconds, a single localized failure can cascade across the network, triggering a widespread, uncontrolled blackout. This is not a theoretical risk. It is the mechanism behind nearly every major power outage in modern history. What is new is that the massive, concentrated loads of AI data centers are creating the exact preconditions that make such cascades more likely. They are systematically eliminating the spare capacity, the safety margin, on the grid. By pushing numerous components to operate near their maximum limits for sustained periods, they are creating a system that is brittle, with no room for error and no ability to absorb a shock. This raises the stakes for everyone. A blackout is no longer just an inconvenience. It becomes a significant threat to public safety and economic activity. When the grid is fragile, a heat wave, a major storm, or a simple equipment malfunction can have consequences that are far more severe than they would be otherwise. The stress introduced by the AI industry's power consumption is therefore not just a problem for the tech companies or the utilities. It is a systemic risk that degrades the resilience of the entire energy infrastructure upon which our society depends. The hidden power bill of AI includes the cost of reduced reliability and the increased potential for catastrophic large-scale failure. Every power grid has a rhythm, a daily and seasonal pulse of rising and falling demand. The highest point of this rhythm is known as peak demand. Traditionally, this peak occurs on hot summer afternoons when air conditioning use is at its maximum, or on cold winter evenings when heating and lighting are turned on. For decades, utilities have built their entire systems around meeting this predictable, weather-driven peak. They maintain a fleet of reserve power plants, often called peaker plants, that sit idle most of the year, ready to be fired up for just a few hours to meet this maximum demand. The new loads from artificial intelligence are now creating a second, entirely different kind of peak. This AI-driven peak is not tied to the weather or the time of day. It can happen at any moment. It might be triggered by a company starting a massive, month-long training run for a new foundation model, causing a sudden, sustained jump of hundreds of megawatts. Or it could be a viral inference application causing millions of users to hit servers simultaneously, creating an abrupt and massive spike in power consumption. This new peak is unpredictable in its timing, its magnitude, and its duration, representing a profound shock to a system built on predictability. This creates a new and dangerous dynamic, the possibility of two peaks colliding. Imagine a hot summer afternoon when the grid is already straining to its absolute limit, with every available power plant running to keep air conditioners on. Now, add the sudden, unscheduled demand from a large AI workload on top of that existing peak. This scenario, a peak-on-peak event, is what grid operators fear most. It pushes the total system demand into uncharted territory, far beyond the planned capacity. In this situation, operators have very few options, and all of them are bad. They may be forced to implement rolling blackouts to prevent a complete collapse of the system. The core challenge is that the grid was never designed to handle two independent, large-scale peak events at once. The entire architecture of supply is based on a single, well-understood maximum load. AI introduces a second, rogue variable that can strike at random. This forces utilities to reconsider the very definition of peak demand. They must now plan for a future where the highest demand on the system is no longer determined by human behavior and the weather, but by the autonomous, unpredictable computational needs of machines. This fundamentally changes the risk profile of the grid, making extreme demand events more likely and more severe. Human society has a natural cadence that is reflected in our electricity usage. We use more power during the day when we are active, and less at night when we sleep. This daily cycle creates periods of high demand and periods of low demand. The electrical grid is optimized around this pattern. At night, when demand is low, utilities perform maintenance, and power prices are often cheaper because only the most efficient baseload power plants are running. Artificial intelligence does not sleep. The massive server farms that power AI models are designed to operate at maximum capacity around the clock, 365 days a year. A training run does not pause at 5 p.m. An inference engine serving a global user base does not get quieter in the middle of the night. This creates a flat, relentless load profile that is completely alien to the grid's natural rhythm. It is a massive block of consumption that is constant, hour after hour, day after day. This erases the traditional valleys of low demand that grid operators have always relied upon to balance the system and perform necessary upkeep. The nightly period of low demand has historically been a crucial time for the grid. It is when reservoirs for hydroelectric dams can be refilled. It is when battery storage systems can be charged. It is when routine maintenance can be conducted on transmission lines and substations without disrupting customers. The constant load from AI data centers consumes this off-peak capacity, reducing the grid's flexibility. It effectively shortens the window available for these critical balancing and maintenance activities, forcing operators to either defer them, creating risk, or perform them during more expensive and disruptive daytime hours. Furthermore, this erodes a key economic lever for grid management. For years, utilities have encouraged large industrial users to shift their power consumption to the nighttime by offering lower off-peak electricity rates. AI data centers, with their need for continuous operation, cannot easily take advantage of these incentives. Their inflexible 24/7 demand profile means they consume huge amounts of power even during peak hours when it is most expensive and the grid is most stressed. This relentless consumption pattern works against the grid's inherent operational and economic logic. As the world transitions to cleaner energy, grids are increasingly reliant on variable renewable sources like wind power and solar power. These technologies are crucial for reducing carbon emissions, but they introduce a new challenge: intermittency. The sun does not always shine, and the wind does not always blow. Grid operators have developed strategies to manage this variability, using flexible resources like natural gas plants, battery storage, and demand response programs. The inflexible, massive load from AI data centers complicates this balancing act enormously. The ideal customer for a renewable-heavy grid has flexible demand, able to reduce consumption when renewable output is low and increase it when supply is abundant. AI data centers are the opposite. They demand a constant, high-quality stream of power, 24/7. When a cloud passes over a solar farm and output plummets, the data center's demand does not change. The grid must instantly find another source to cover the lost power. For every megawatt of AI demand added, a corresponding megawatt of firm, dispatchable capacity must be available. Today, that backup most often comes from natural gas-fired plants. Rapid AI growth, even with renewable purchase agreements, can paradoxically increase reliance on fossil fuels. A data center may have a contract for solar power, but the grid still burns more gas to guarantee 24/7 reliability, especially at night when solar is unavailable, but AI workloads continue. This creates a structural barrier to deep decarbonization. More wind and solar alone cannot solve the problem posed by giant, inflexible loads. It requires massive parallel investment in energy storage, like batteries, on a scale not currently feasible. Without storage, AI servers' constant thirst tethers the grid to conventional plants, slowing the transition to a fully renewable system. AI's power demand is fundamentally at odds with weather-dependent supply, creating deep-seated tension at the heart of the energy transition. Beyond just generating watts, traditional power plants provide a hidden but vital service to the grid: physical inertia. The massive spinning turbines in a coal, gas, or nuclear power plant act like giant flywheels. Their immense rotating mass stores a huge amount of kinetic energy. This physical inertia helps to stabilize the grid's frequency, which in most of the world must be kept at a precise 50 or 60 Hz. If there is a sudden drop in supply or a spike in demand, the inertia of these spinning generators gives grid operators a few crucial seconds to react before the frequency deviates to dangerous levels. It is a free, built-in shock absorber for the entire system. Renewable energy sources like solar and wind do not provide this service in the same way. Solar panels have no moving parts. Wind turbines have spinning blades, but they are connected to the grid through power electronics and do not contribute the same kind of stabilizing inertia as a multi-ton conventional turbine. As we shut down traditional power plants and add more renewables, the total amount of physical inertia on the grid is decreasing. This makes the system lighter and more fragile, more susceptible to sudden shocks, and more difficult to keep in balance. The grid's frequency becomes more volatile and can fluctuate more rapidly. Into this increasingly fragile system, we are now adding the spiky, unpredictable loads of artificial intelligence. An inference-driven demand surge, which appears on the grid almost instantaneously, is exactly the kind of shock that a low-inertia grid is least equipped to handle. Without the stabilizing effect of large spinning generators, such a sudden load can cause a rapid and dangerous drop in frequency. If the frequency falls too far, automated safety systems begin to disconnect parts of the grid to protect equipment, leading to blackouts. The combination of declining inertia and rising AI-driven volatility is a recipe for instability. To compensate for this loss of inertia, grid operators must find new ways to provide stability. This can involve installing large banks of batteries or other advanced technologies that can react in milliseconds to stabilize the frequency. However, these solutions are expensive and are not yet deployed at the scale needed to counteract both the retirement of conventional plants and the addition of massive new AI loads. The fundamental physics of the grid are changing. The invisible, stabilizing force of inertia, which we have taken for granted for a century, is diminishing just as a new, powerful, and destabilizing force is emerging. To handle the highest hours of demand each year, utilities rely on a special category of power plant known as a peaker plant. These are typically fueled by natural gas or oil. They are designed to start up very quickly, go from zero to full power in a matter of minutes, and then shut down again once the peak has passed. Because they run so infrequently, they are often older, less efficient, and emit more pollution per unit of electricity generated than modern baseload plants. They are an expensive but necessary tool for ensuring reliability. The unpredictable demand spikes created by artificial intelligence workloads are putting these peaker plants under a new kind of pressure. A sudden surge in inference demand or the start of a new training model can force a utility to fire up its peaker plants at a moment's notice, at any time of day or night, and at any time of year. This transforms them from a tool used for a few dozen predictable summer afternoons into a resource that must be on standby constantly to react to the whims of AI computation. This increased operation means they burn more fossil fuels, produce more emissions, and drive up the overall cost of electricity. This creates a difficult dilemma for utilities and regulators who are trying to move towards a cleaner energy future. Many long-term plans call for the gradual retirement of these fossil-fueled peaker plants to be replaced by batteries and other clean alternatives. However, the sudden arrival of massive AI loads makes these plants more critical to grid reliability, not less. Utilities are now finding that they cannot retire these older, dirtier plants as planned. In some regions, they are even being forced to build new gas-fired peaker plants specifically to serve the volatile demand from data centers, locking in decades of future fossil fuel consumption. This is one of the deepest contradictions of the AI energy story. Technology companies may be purchasing renewable energy to power their data centers, but the volatile nature of their demand is increasing the entire system's reliance on the most flexible and often most polluting form of fossil fuel generation. The growth of artificial intelligence is therefore acting as a powerful brake on the transition away from fossil fuels, creating an operational and environmental paradox that is rarely discussed. The connection between electricity and water is one of the most critical but least visible aspects of our energy system. The vast majority of power plants around the world, coal, nuclear, natural gas, use a process called thermoelectric generation. They burn a fuel to create heat, which boils water into steam, which then spins a turbine to generate electricity. After the steam passes through the turbine, it must be cooled back down into water to be used again. This cooling process requires a tremendous amount of water, which is typically drawn from nearby rivers, lakes, or oceans. This makes the power grid highly vulnerable to changes in water availability. During a drought or a heat wave, water levels in rivers can drop, and the temperature of the remaining water can rise. When the water source is too low or too warm, power plants may be forced to reduce their output or even shut down completely to comply with environmental regulations and to avoid damaging their own equipment. The massive, unceasing power demand from AI data centers adds a new layer of risk to this already fragile relationship. An AI training run that requires hundreds of megawatts of continuous power for a month is also implicitly demanding millions of gallons of water for cooling at the power plant. If a drought forces that power plant to curtail its operations, it directly threatens the uptime of the data center, creating a collision between computational demand and environmental limits. This interdependence runs both ways. Data centers themselves are also massive consumers of water for their own internal cooling systems, especially in hot, dry climates where many are located. They draw this water from the same local supplies that communities and agriculture depend on, supplies that are already under stress. The hidden power bill of AI is therefore accompanied by a hidden water bill. The industry's growth is placing a dual strain on two of our most essential resources, creating a feedback loop where the demand for computation exacerbates both energy and water scarcity, especially in the regions most vulnerable to a changing climate. We have traced the journey of electricity from its source to the processors that power the new age of machine intelligence. This journey has revealed a system under a form of pressure it was never designed to withstand. The silent, exponential growth of artificial intelligence is not just creating a new category of electricity demand. It is forcing a systemic reckoning with the physical infrastructure that underpins our digital world. We have seen how the immense concentrated loads of AI data centers can overwhelm local distribution networks, the final, fragile link in the power delivery chain. We have examined how these loads accelerate the aging of critical transformers and substations, pushing them toward premature failure and creating supply chain bottlenecks for their replacement. The stress accumulates, moving up the hierarchy of the grid to clog the major transmission arteries that function as the backbone of our regional power systems, limiting the flow of energy and creating widespread congestion that affects all users. This investigation has shown that the challenge is not just about generating more power. It is a more fundamental problem of pace and design. The breakneck speed of technological innovation in the AI industry is profoundly mismatched with the slow, deliberate, and decade-long timescale of energy infrastructure development. This temporal gap creates a constant state of reactive crisis for utility planners, forcing them to chase demand rather than strategically plan for it. The result is a less efficient, more expensive, and more brittle grid where short-term fixes take precedence over long-term stability. The hidden power bill of AI is therefore far more than the sum of the electricity consumed by servers. It includes the cost of emergency grid upgrades, the accelerated depreciation of legacy equipment, and the economic distortions created by transmission bottlenecks. It is a bill that accounts for the increased reliance on fossil-fueled peaker plants and the compounded strain on water resources. This is a systemic cost, distributed across the entire infrastructure and ultimately paid by society as a whole, often through higher electricity rates and a subtle but significant decrease in the overall reliability of the power supply we all depend on. The systemic pressures we have analyzed are now beginning to manifest as tangible, realistic risks to the stability of our power supply. At the lower end of this spectrum is a simple degradation of power quality and reliability. This can appear as voltage sags or brief flickers in the power supply, minor annoyances for a household, potentially damaging for sensitive industrial or medical equipment, and a clear warning sign of a system operating too close to its edge. A more significant risk is the increased probability of localized blackouts and regional blackouts. The concentration of AI data centers creates the perfect conditions for cascading failures. By eliminating safety margins on local and regional networks, a single equipment failure, a common occurrence, is more likely to trigger a domino effect that could now plausibly cascade into an outage affecting an entire metropolitan area for hours or even days. The resilience of the grid is being traded for computational capacity. This increased fragility makes our energy systems far more vulnerable to external shocks. An extreme weather event, such as a prolonged heat wave or a severe winter storm, becomes a much more dangerous scenario. When the grid is already heavily loaded by the constant demand from AI, it has less ability to cope with the additional surge in demand from air conditioning or heating. This peak-on-peak scenario dramatically increases the likelihood that utilities will be forced to implement rolling blackouts, not as a last resort, but as a standard operational procedure to prevent a complete system collapse. The ultimate and most severe risk is a large-scale, long-duration blackout. While still a low-probability event, the underlying conditions that lead to such failures are becoming more prevalent. The combination of aging infrastructure, declining system inertia from the loss of traditional power plants, and the addition of massive, volatile AI loads creates a grid that is fundamentally less stable than it was a decade ago. The quiet hum of servers in a data center is directly contributing to a future where the reliable supply of electricity, the foundational infrastructure of modern civilization, can no longer be taken for granted. The potential for large-scale failure is now a core planning reality. The rise of machine-scale electricity demand is forcing a fundamental change in the operational logic of the power grid. For a century, the grid was designed and built to serve human patterns of settlement and activity. Power flowed to cities, industrial centers, and residential areas. Utility planning was an exercise in demography and economics, forecasting population growth and business development. Today, a new and powerful organizing principle is emerging. The flow of power is increasingly dictated not by where people live, but by where computation happens. The energy map is being redrawn by the needs of machines. This new logic is creating a geographic shift in energy infrastructure development. We are witnessing the rise of new load centers in formerly rural or low-demand areas, like Northern Virginia, Central Washington, and Arizona, chosen for their access to land, water, and fiber optic cables. The singular need to power massive data center campuses in these locations is now the primary driver of new investment in transmission lines and power plants. Public infrastructure planning is becoming increasingly subservient to the private locational decisions of a handful of technology companies, reshaping regional economies and energy landscapes in the process. This shift also transforms the nature of risk management for grid operators. Their primary challenge is no longer just how to manage predictable, weather-driven peaks. They must now contend with the unpredictable, spiky, and inflexible demand profiles of AI workloads. This introduces a profound level of uncertainty into system operations. The grid, a system that requires real-time balance and stability, is now directly exposed to the volatility of the digital world. The viral launch of a new application, the competitive race to train larger models, the minute-by-minute behavior of millions of users. The abstract world of software is now a direct input into the physical management of the power system. Ultimately, this requires us to treat machine-scale electricity demand as a core infrastructure planning problem on par with transportation, water, and communications. It can no longer be viewed as simply another customer to be served. The sheer scale and unique characteristics of this load require a more integrated approach to planning, one that aligns technology development with the physical constraints of our energy and environmental systems. Without this, we risk building a future where the growth of artificial intelligence is fundamentally limited by the carrying capacity of the physical world. Or worse, a future where the pursuit of that growth destabilizes the very systems that sustain us. The story of artificial intelligence and electricity is one of a hidden relationship, an unseen equation that connects the seemingly weightless world of data to the heavy industrial reality of power generation. Every query we make to a generative AI, every recommendation served to us by an algorithm, every scientific discovery accelerated by machine learning adds another term to this equation. On one side is the promise of innovation, convenience, and progress. On the other side is the physical cost, measured in megawatts, in aging infrastructure, in strained resources, and in systemic risk. For a long time, we have focused only on the first half of this equation. The purpose of this examination has not been to halt progress or to demonize a new technology. It has been to make the second half of the equation visible. It is an argument for a more complete and honest accounting of the true cost of an artificially intelligent world. This requires moving beyond a narrow focus on the capabilities of AI and acknowledging its fundamental dependence on the physical systems of the planet. The challenges of grid stability, infrastructure capacity, and resource management are not secondary issues to be solved later. They are foundational constraints that will shape the future trajectory of AI development. The path forward is not a simple one. It involves difficult conversations and complex trade-offs between technological ambition and physical limits. It requires a new level of collaboration between the fast-moving tech industry and the slow, deliberate world of utility regulation and infrastructure planning. It demands that we ask difficult questions about how we prioritize our energy resources and who should bear the costs of this new industrial revolution. Should communities absorb the grid stability risks created by a single industry? How do we balance the demand for computation with the urgent need to decarbonize our energy supply? These questions do not have easy answers, but acknowledging them is the necessary first step. The silent hum of progress is growing louder, and it is no longer possible to ignore the strain it places on the infrastructure that powers our lives. The hidden power bill is coming due, and understanding its full cost is essential if we are to build a future that is not only intelligent, but also sustainable and resilient. The unseen equation of energy and computation must be brought into the light, not as a matter of technical debate, but as a central question for society in the 21st century.